Okay, we have already 5 minutes delay. There are some more people. Okay, let's start our next seminar after more than 1 month break. We have a very interesting talk, I hope, about bootstrap program for geographic defect. And the speaker will be a Professor Xinan Zhou. Please, 1 hour.
Okay, thank you very much for the invitation and the introduction. So I'm very happy to be here to talk about some of my recent works. So this is going to be a review talk about several papers written with different collaborators. So Junding Chen is my student. Alish Jamir and Hinek Paul, they're postdocs in Europe, and also with Fernando Alday, who's in Oxford, and also Yunfeng Jiang, who is a professor at Southeast University. So my talk today will mostly focus on the first, second, and the fourth paper, but will also mention how the techniques apply to other setups, which are discussed in the third and the fifth paper. Okay, so yeah, let me start with some general motivation. So we all know that defects are interesting extended objects which can be found in many different physical systems. And there are many motivations for considering defects, both from the experimental point of view and also from the formal side. So experimentally, there are many things such as impurities, finite size effects, and domain walls. They can all be characterized as defects. And formally speaking, we know there are Wilson loops, symmetry generators, and also deep rings. They are also defects. So the reason that defects are interesting is because when we introduce defects, we can make the dynamics of the system richer. So on the one hand, when we introduce defects, they are usually new degrees of freedom that are localized on these defects. So we introduce new degrees of freedom. On the other hand, when we insert defects, the symmetries of the system are usually partially broken. And the consequence of that is that we can have more observables which are otherwise prohibited by the system, the symmetry of the system. So for example, in an empty flat space, usually we don't have one-point functions. The only non-trivial one-point function is just the identity operator. However, if we have defects, already one-point functions can exist. And these defects, usually they can be, we can talk about defects in just general QFTs, but in this talk, I'm going to focus on defects in conformal field theories. And in particular, I will look at these defects which occupy RP subspace of the total d-dimensional spacetime, RD, okay? And also, I will assume the spacetime is the Euclidean. So this is a sort of like a restricted setup. However, we'll see it's still quite general and covers many interesting cases. So we can, so usually when we talk about defects, we would assume the dimension of the defect P is greater than or equal to 1. So for example, for P goes to 1, we have line defects, and the most well-known examples are Wilson loops and 't Hooft loops, or they are generalizations where you have both the electric and the magnetic charges. And for p equals to 2, we get surface defects, and we can continue by increasing p until we reach p equals to d minus 1. So this is codimension 1, and that corresponds to boundaries or interfaces. So far so good. Do people have any questions at this point? Okay, so yeah, just interrupt me whenever you have anything you want to ask. Okay, so I just said that usually we consider the case where p starts from 1 and goes all the way to d minus 1, but we can actually also further extend this list of defects by including the ones with dimensions which are smaller than 1. And so these numbers, they seem a bit exotic, but actually they can be easily understood with the help of horography. So the reason is that usually when we do ADS-CFT, objects in the conformal field series will gain one extra dimension by moving into the bulk. So here, let me just give you two examples. In the familiar example of n equals 4 super mils, where the value of p is smaller than 1. So one example where the defect dimension is -1 is when we put this n equals 4 super mils theory on a 4-dimensional projective space. So the reason this can be viewed as a -1 dimensional defect is because this RP4 theory is actually just due to the usual ADS phi times S phi theory, but with a Z2 quotient, okay? And this Z2 quotient actually has a fixed locus when acting on the geometry. And this locus is a 2-sphere sitting inside the 5-sphere. So this 2-sphere is actually just sitting at the points in this ADS 5 factor. So a point is 0-dimensional, right? And it gains the dimension by going to ADS. So that's why we stay on the boundary. It's actually -1 dimensional. Another example is the giant graviton correlators, which has dimension 0. So the reasoning is similar. So giant graviton operators, we know they are very heavy objects. So in the ADS, they just move along a geodesic line connecting two boundary insertion points. And the line is 1-dimensional, therefore, from the boundary perspective, it's 0-dimensional. I will briefly mention these two setups towards the end of my talk. But for the most of my talk, I'm going to focus on these more conventional defects with dimensions greater than or equal to 1. Any questions? Okay. So let me give you one more motivation for why considering defects are interesting. So actually, we can view any quantum field theory as a defect CFT by putting the theory in ADS space. So the reason we can view it like that is because when we put a QFT in ADS D, the system will have the same conformal symmetry as a D-dimensional CFT with a boundary. This symmetry comes just from the isometry of this D-dimensional ADS space, and doesn't matter if the QFT is tuned to its critical point or not. And more generally, we can put a QFT in a space that has an ADS-D factor and an SQ factor. Okay, then the isometry of the system will be the same as a D plus Q dimensional conformal field theory with a codimension Q plus 1 defect. So by doing this, we can now apply these techniques for studying defect CFTs to any QFT. And what's nice about this setup is that the radius of ADS gives you an gauge invariant IR regulator. And we can study different phases of the QFT by dialing this radius. Okay, so in my talk today, I'm going to mostly going to focus on defect CFTs which have holographic duals. And I'm further going to consider the simplest case where the defects are due to an ADS P plus 1 dimensional subspace inside ADS D plus 1. And in these holographic defect CFTs, the most basic observables are correlation functions of local operators. So here I'm going to focus on these correlators where the operators are inserted away from the defects, okay? And physically, these correlation functions, they correspond to form factors in ADS, where you have massless particles scattering with an extended object. So this extends the usual story where you consider these holographic correlators. They are due to scatter amplitudes. Now they're due to form factors. So in this talk, I'm going to I will not get into too much technical details. Of course, we can discuss more if you're interested after talk. But I'm mainly going to just give an overview of some of these techniques that we recently developed. So these are some analytic bootstrap techniques for computing holographic correlators in defect CFTs. So the reason why we are trying to do bootstrap is because usually if we are trying to use a diagrammatic approach to compute these holographic correlators, it is very cumbersome. So even without defects, people first studied, 4-point functions. Let's say ADS phi times S phi to be supergravity. Already there, you find the story is extremely complicated. For example, if you want to compute 4-point functions at tree level, you find the general vertices, which you need to use as an input, take 14 pages to write down. So it's sort of like quite hopeless if you want to just follow the traditional diagrammatic method, step by step. So, but then it was realized actually these input, they are unnecessary, and the holographic correlators can be more efficiently fixed by just imposing symmetries and consistency conditions. So that is bootstrap. So we are going to extend this story from defect-free CFTs to those involving defects. And I'm going to focus on the simplest non-trivial defect correlator, which is 2-point functions of operators inserted away from the defects. So these 2-point functions, they are not completely fixed by the remaining symmetries. So it's unlike 1-point functions, which is completely determined up to just an overall constant, okay? And I'm going to present bootstrap techniques for computing these holographic correlators, both at tree level and loop level in ADS. And I'm also going to talk about how to go beyond supergravity description and consider their stringy corrections. So that's a rough plan of this talk. So if there are no questions at the moment, I'm going to start with, yeah. Okay. So to demonstrate these methods I mentioned, I'm going to look at a specific theory. So here, I'm just going to choose a theory for kinematic simplicity. So this is a theory of the theory in 6 dimensions with 2,0 superconformal symmetry. And I'm going to consider in the theory surface defect, which is half BPS. And I should mention that this theory is an intrinsically strongly coupled theory because it does not have a Lagrangian description. So there's no other way to study it from the boundary field theory perspective. So I'm just going to use this as a concrete example to illustrate these techniques, but these techniques are completely general and can be applied to many other interesting cases, and I'm going to mention some of these other examples a bit later on. Okay, so let me just say a few words about the theory we are looking at. So this system can be realized by using a large number of M fibrins, so N is large, and together with some probe M2 branes. So here for simplicity, I'm just going to take one probe M2 brane, okay? And the dual geometry of the setup is just you have an ADS3 subspace inside of ADS7 times S4. Okay, so this ADS 7 times S4 is the usual story. So that comes from these M fibrins. And this ADS 3 is just for the volume of this M2 brane, which is now embedded in this curved ADS 7 times S4. We are also going to consider the limit where N is large. So this is approximated by supergravity. Now for ADS 7 times S4, we know this story very well. So we have 11-dimensional supergravity, and the Kluser-Klein modes of this 11D supergraph field corresponds to these half BPS multiplets in the 60 SCFT. And their superconformal primaries are some scalar operators, which I'm calling here SK. So they have protected conformal dimension proportional to their KK level, and they transform in some symmetric traceless representation of SO5 asymmetry. Okay. Now, on this ADS3 slice, where you have this M2 brane, you have some localized degrees of freedom. So these are the fluctuations of this M2 brane, and they are coupled to the bulk. So the action takes the following schematic form. So you have a bulk part. So here to emphasize the N dependence, I've extracted them here. So the bulk part is proportional to n cubed. And then you also have a brane part, which is proportional to n, and it has both the defect fields and also the bulk fields. Okay. Now from this n.
Sorry, Xinan, may I ask you a question?
Yes.
I'm a bit confused. Where do you get these factors n cube and n?
So one way to see that is like a central charge, for example. Sorry. I thought, was there another comment?
No, it's okay. Please continue.
Okay, sorry. Yeah, so yeah, or you can just look at like the tension of, for example, this is brane, so the tension is proportional to n.
But sorry, it's okay. So you have one brane with n.
So n is the number of M fibrins.
So can you just comment how this one brane gets this n? Because you have probe M2 brane, how it gets this n in the tension?
I think that's the usual story. Like it doesn't really matter if it's M2 brane or it's a D brane.
Yeah. No, I'm not about M2. I'm just saying that you have M5 branes there, n of them, and then I can understand. But I think that depends on how are they coupled one to each other, yeah?
I think so, yes. But yeah, so I don't know that off the top of my head, but it's actually doesn't matter so much. You can just assume like it's some general power of n.
Okay.
So yes, yeah. So it doesn't quite matter for what I'm going to discuss. Yeah.
Okay. Thank you.
Okay. Thanks for the question. So right.
I also have a question. So I'm not very familiar with the topic, so I'm sorry if my question is very basic. So you said that this 6D theory has no Lagrangian description, right?
Right.
Okay, so this action that you write at the end would be some dual action for the model, or?
Oh, right. Yeah. So when I say there's no Lagrangian, it's from the 6D perspective. But so this action is from the 11D perspective, like in the dual description.
Okay.
Yeah. So from the dual perspective, it has a Lagrangian. It's just the supergravity coupled to some localized degrees of freedom on a brane. Yeah.
But using somehow the duality, can you really infer what is the expression for the Lagrangian in the strongly coupled theory or not? Like, can you get some effective?
Not really, because this is also, so yeah, this theory is a bit special in the sense that there's actually no coupling. There's no marginal coupling which you can tune. It's not like 4D n equals 4. So there's not a like weakly coupled limit where you can start with. Yeah.
Do you have some equation that tell you what is the dynamics of the system?
So yeah, you may take this as like a definition. So this is like weakly coupled. So this is just the action of 11D supergravity. You can write down all the fields, how they're coupled. Yeah. And then you have like some brane, like it has some kinematic term, and then it also coupled to the bulk. Yeah.
Okay, I see. So you just work on the dual side, let's say.
Yeah. So right. So yeah. So we are just going to work from this bulk perspective. Yeah.
Okay, I see. Thanks.
Yeah. Thank you for the question. Okay. So from this independence, so it doesn't really matter what this power is. So we can do the usual 1/n counting, right? So we can work out the propagators, the vertices, like how they depend on these overall powers of n. And then you can do this 1/n expansion for 2-point functions. And the first few orders, they look as follows. So let me also explain a little bit what this diagram means. So this circle here stands for the ADS, okay, the boundary of ADS. And this blue line corresponds to this defect, this ADS3 subspace. Now, a leading order, what you get is just the free propagator. This line here, it does not even see the defect, okay? Now, at the next order, you start to have contributions coming from just two disconnected one-point functions, okay? And these two orders are trivial because, these are just fixed by symmetry. The non-trivial contribution comes from the next order, which is the sum of all these tree-level interactions with the defect. So you can exchange a field in the bulk channel, or you can exchange a defect fluctuation on the defect, or you can have these counter interactions. And then you can go to even higher orders in 1/n, and then you have these one loop, more complicated one loop processes, okay? So these two orders are what I'm going to talk about in the next few slides. So let's first look at tree level, okay? So at tree level, the most difficult part is to determine the vertices. The reason it's complicated because you have infinite many Kanuta-Klein modes. So you have infinite many vertices to determine. However, the point is that we don't really need to do that because they're essentially just determined by supersymmetry. And that's the key idea of the bootstrap method. So let me now schematically outline how this bootstrap method works, okay? So the starting point is an onset. So for any through the client level, K1 and K2, we can write down an onset as a sum of all possible Witten diagrams. So it includes all the three types of Witten diagrams that is introduced. And we are going to multiply them with some unknown coefficients. Okay, so here important point is that the number of diagrams in a certain two-point function is always finite. So this essentially just follows from asymmetry selection rules because all these fields exchanged, they carry some asymmetry, irreducible repetition, okay? So already tensor product of asymmetry repetitions tells you that the number of repetitions which can appear is finite. Okay. Now, in addition to these Witten diagrams, which is sort of like space-time part, there's also an asymmetry polynomial corresponding to the information of exchange asymmetry repetition. So more precisely, I have a Witten diagram multiplied by an asymmetry polynomial, then it's multiplied by some just the numerical unknown coefficient. Okay, so that's the ansatz. Now, the next step is to evaluate this ansatz in terms of elementary functions. And there are standard tricks by now to do that. So there was a paper from the beginning of ADS-CFT, which teaches you how to compute Witten diagrams, and you can recycle that techniques, and you can show that all these exchange Witten diagrams can be reduced to just a finite sum of these contact Witten diagrams. Now, these contact Witten diagrams, they're very simple. They can just be evaluated in the closed form as some 2f1 functions of the conformal cross ratios. So these conformal cross ratios are defined as some combinations of their coordinates. And you can also rewrite them in a more familiar manner in terms of z and z bar. So the meaning of that, these variables is roughly that you insert the defect as 0 and infinity, and you use conformal symmetry to fix one point to be at 1, and then there's another one which you cannot fix that has coordinates z and z bar. Okay, so using this trick, you can evaluate all these Witten diagrams as some known function of z and z bar. And then comes the last step. The last step is that we impose constraints from supersymmetry. And these constraints are known as superconformal word identities. And these word identities, they take a very simple form. So it's just a differential constraint. So z is this conformal cross ratio. And this omega here is the asymmetry analog of that, okay? And these word identities just tells you how the dependence on these cross ratios are related on this slice where z is set to omega. So it's very straightforward. You write an onset, you evaluate it, then you impose these superconformal symmetry constraints. You find it very remarkably, all these unknowns you introduced here are fixed. So that's how you can compute these defect correlators without starting from the details of the effective Lagrangian. Okay, now to show you the result, I want to go on a little detour to introduce the so-called mailing space. So this mailing space is actually very similar to momentum space we have in flat space. But we all know that you cannot really have a momentum space in ADS because translation symmetry is broken in ADS, right? So you cannot just do Fourier transform, but you can do mailing transform. So Fourier transform corresponds to translation invariance, and the mailing transform really corresponds to dilatation invariance. Okay, and dilatation is of course part of conformal group, so that's why it's useful. So concretely, what do we mean? So we can just write this two-point function, which is a function of cross ratios, as a twofold inverse Mailing transform. So these cross ratios B and D, they are related to this Z and Z bar in some way, but it doesn't really matter what the details are. So what we need to know is that so when we take the bulk channel limit, where like these 2 points are squeezed together, this cross ratio B goes to 0. If it takes the other limit, where this operator is moving towards the defect, then the other cross ratio D is going to 0. Okay, so these two limits correspond to bulk channel limit and the defect channel limit. And here I also defined some gamma function factor. So you can just understand that as part of the definition. So doing that is very nice because it gives you this Mailing amplitude that you can intuitively think of as a form factor in flat space. Okay, so in particular, these dual variables delta and gamma, they are just due to these Mandelson variables. So you have two particles with a momentum P1, P2 scattering with this defect here. So you have two channels, and these, roughly speaking, these Mandelson variables are just delta and gamma. To see why this formula isn't useful, you can just look at individual Witten diagrams. You find that contact Witten diagrams, they just become polynomials. And these exchange Witten diagrams will have poles in these Mandelson variables. So this is very much similar to what you have in flat space. So I'm not going to show you more details. I'm just going to tell you that if you take the potential space result obtained from Bootstrap and you translate into Mailing space, you find that the final result is super simple. So for arbitrary K1 and K2, you find that the Mailing amplitude just takes this form as a sum over over simultaneous poles with some coefficient, with some numerators, which are polynomials of the asymmetry cross ratio. Okay, any questions for the tree level bootstrap? Okay, so right. So let's now go one step beyond and consider loop level corrections. So they correspond to these diagrams. Now this is much trickier because even for the simplest one loop diagram, we don't really know how to compute. Okay, yet we can still compute these correlators at one loop by extending the unitarity method in flat space. So we call this the ADS unitarity method. And actually, it was first extended to CFT 4-point functions in defect-free CFTs in a paper by Aharoni, Aldai, BC, and Permuter. And the idea is actually similar to flat-based amplitudes. So the idea is that we can obtain these loop-level corrections by gluing together tree-level results. And I want to, okay, and this method can also be extended to defect correlators, as we did in this paper from last year. So the main idea can already be seen at a diagrammatic level. So if you look at these one loop diagrams, you find that we can cut these diagrams to obtain diagrams at lower orders. So for example, if you take this diagram, you cut along this yellow line, you find it becomes a defect-less 4-point function at tree level and disconnected defect 2-point function. Or you can take some of these diagrams, you can cut vertically, and you find you just get tree-level defect 2-point functions. And of course, there's these diagrams which you can cut in both ways. Now, this is of course a bit misleading because it's not very accurate. So the more accurate statement should not be understood, at the level of diagrams. Actually, I will show that the more precise statement is that these correlators can be cut in both ways. So you can either obtain it by gluing together a defect-free 4-point function at tree level with a disconnected defect 2-point function, or you can get it by gluing together two tree level defect 2-point function. And that to give you the same result is actually a non-trivial consistency condition. Okay. So this is a very schematic picture. Now let me be slightly more precise. More precisely speaking, and also at a more technical level, this gluing is done in terms of certain singularities. So we call these singularities leading logarithmic singularities. So what we mean by that is, so these singularities occur when you take the limits I mentioned. So you take B or D goes to 0, and you will find that the correlators will develop some logarithmic singularities. For example, log B and log D squared. Okay, and by leading, I mean we are going to take these singularities with the highest power. Okay, so what I said about gluing actually happens in terms of these leading logarithmic singularities. And to see this gluing, we need to decompose these singularities into conformal blocks. And after some simple manipulations, you find that these decomposition coefficients can be rewritten as the coefficients which appear at lower orders. So for example, here you find these coefficients exactly becomes just the tree level 4-point function times disconnected 2-point function divided by disconnected 4-point function. And similarly for the defect channel. Of course, there are actually, in the slides, there are many things I'm sweeping under the rug. So there's one important subtlety is the mixing of operators, because you find that there are actually many double trace operators which have the same engineering dimension. So they're really mixed together, and you need to do some sort of unmixing in order to really have this picture of tree times disconnected. Okay. Right. So let me just quickly, summarize what we're doing here. So what we are doing here is that we are recycling what we got at tree level to compute certain limits of this one loop correlator. And the next thing we need to do is to complete these singularities into the full correlator. Then we can say we have computed one loop correlator, right? And the most convenient way to do that is, again, in embedding space. So essentially, what we did is that you can write down an ansatz with the following form. It's a simultaneous pole. It's a double infinite sum with some numerators, which you assume to be just numbers. And then you solve this ansatz, and you come back to check that it's actually the right ansatz, okay? So I'm not going to go into the details because of the lack of time. I will just say that these coefficients can be worked out in general and take some form of some 3f2 of m and n, okay? So this is how you can go beyond tree level and bootstrap loop level correlators, even though we don't really know how to compute any single Witten diagram at loop level. Okay, so I have covered two things. Now let me move on to the last thing, which is stringy correction. And before I do that, I first want to talk about flat space limit, which will be very helpful for us to studying stringy corrections. So what's the idea of a flat space limit? So the idea is very simple. So we can look at the limit where the radius of ADS goes to infinity. And in this limit, ADS is essentially a flat space. So therefore, we expect our correlators in some limit will give rise to the flat space amplitudes. And this is actually true in all representations, but it is particularly convenient to implement in mailing space. And in CFTs without defects, it's actually already known how to do that in this paper by Joao Panadonis from 2010. So he found that this flat space amplitude is related to the high energy limit of mailing amplitudes by a Borel transform. Of course, high energy limit is very natural, right? Because if you go to high energy, you're probing small scales, so everything looks approximately flat. Now, for defects, Fernando and I found a very similar formula in mailing space. It also takes the form of Borel transform. And also, it depends on the high energy limit of the mailing amplitude.
Xinan, there is some question here in the chat.
So how do I see the question?
Well, I can read it to you.
Okay. Yes, yeah. What? Yes, right. So the Feynman rules, these vertices is what you would otherwise need if you want to follow, how the calculations are done in textbook. But the point here is that we don't want to do that because it's very complicated. So it turns out, these symmetries and the consistent conditions are sufficient to determine these amplitudes as a whole, yeah? And once you get the result, you can work backwards and you can extract the details of how particles interact with each other. You can extract these vertices. I'm not sure if the question, yeah, I'm not sure if the person is happy with it. Okay, anyways, let me maybe move on first. Okay. So, right, now we can talk about stringy corrections. So the flat space formula I mentioned earlier is useful because in flat space, we can compute a lot more. So we actually know how to compute the amplitude, for example, for this process here. So you have two closed strings interact with a deep ring. So you can actually compute it, and you find the answer is given as follows. It looks actually very similar to Veneziano amplitude, apart from some factor, polynomial factor depending on -1 variables. So by taking the flat space limits, we can actually already use the information from flat space, and that will fix us some of the stringy corrections. So now to make this discussion a bit more concrete, I'm going to look at the defect correlator in n equals to 4 super mils, where the defect is a 't Hooft line. So this 't Hooft line is due to a D1 string in the bulk. Okay. Right. So in the literature, actually only the case of Wilson line has been worked out. So this is in Jimenez-Gras paper. But at the supergravity level, the answer is actually the same, also for 't Hooft line. The reason is because you can show that tree level, because everything is fixed by superconformal symmetry, and the ansatz for these two cases are actually the same, and therefore you would get the same results. The only difference would be the overall constant would depend on whether it's would be different depending on what kind of line defect you have. Okay, so I'm not going to show you the mailing amplitude I'm only going to show you the high energy limit of the median amplitude. So if you take both gamma and delta large, you find it has the following form. And then you can plug into our formula, and you can compare then with this flat space string theory amplitude, and you find very precisely the leading order term. The leading order term when L string goes to 0 is reproduced. Okay, so this is this is sanity check. Now you can go on to look at subleading terms when L string goes to 0. Okay. Corresponding to that, the mailing amplitude also has a expansion. So this S goes to 0 corresponds to just a large Hofft limit, large Hofft coupling expansion. So here, let me explain a bit more in detail. So here you first have a supergravity solution, and then it's multiplied by some known function of the Hofft coupling. The reason, like you always have such a term, is because the one-point function receives corrections in 1 over lambda, and that persists to all orders in 1 over lambda. Then you have these additional terms which corresponds to higher derivative interactions, higher derivative contact terms. So this, right, so I think it goes all the way here. So this one is 8 derivatives, this is 6 derivatives, this is 4 derivative, I think. Yeah, and these building blocks, these M, L, they are some solution. So they are, first of all, they are a combination of these contact region diagrams, and they solve their individual solutions which solve the superconformal word identities. Okay, so you find when you increase the number of derivatives, you find there are more and more solutions, and moreover, this L labels the degree of this ML polynomial when minus some variables go to infinity. Okay, that's yeah. Well, how it scales at large energy. Okay. So right, so you find, as you increase the order, you find that there are more and more solutions. So you have more and more parameters which you want to fix. Now, to fix these parameters, we can first use the flat space limit formula, right? And you find in the flat space limit only at each order, only these terms that grows the fastest will survive this limit. So by just using by this amplitude, you can already fix all these terms, like, here L equals to 3, these 2 terms, and here all these L equals to 4 terms. But still, you find at higher orders, you have more coefficients which you cannot fix. And to fix these numbers, we can use additional constraints from supersymmetric localization. So these constraints are in the form of certain integrated correlators, and that's been studied by a number of people listed here in the defect context. So roughly speaking, what they're doing is that you can, take this mass deformed partition function, which you can compute using localization, and you take derivatives, either respect to the mass or respect to the coupling, that will bring down operators. So you take 2 derivatives, so you get a 2-point function, but this is integrated over, okay? So, right, so this is the precise relation between this derivative of partition function and integrated correlators. And these things are computable for even for finite n, okay? And here we're just looking at the supergravity limit. So it's large n and large lambda. So using these as additional inputs, you can compare this with these ansatz, and you can fix the sum of the remaining coefficients. So in our paper with Fernando, we actually fixed all these coefficients up to 8 derivatives in the higher derivative coupling contact vertex, up to 1 linear combination at the highest derivative order. Okay. Okay, so right, so I've introduced all these techniques. Now let me mention a few other systems which I think are more interesting. So as I said, like these techniques are very general and they can be applied to essentially any defect system which looks like a probe-RAN. And here I'm going to highlight the results for two cases with unconventional, defect dimension, where p is -1 or 0. So let's first look at the p equals to -1 case, which is n equals 4 super Young mills at p4. And here we are also going to focus at the strong coupling. So you find, as I mentioned earlier, in this case, the defect is really just a point in ADS, right? So the Witten diagrams are slightly different. So you need to end at a point instead of a surface. And here, this blue line or this shaded region is essentially telling you you are doing a Z2 quotient of ADS. So you only have half a space. But anyways, like these Witten diagrams, which take the following form, you can also compute it using the method of images. And contact Witten diagram, you can also compute. And what's very nice about this system is that these Witten diagrams are extremely simple. So you find the contact Witten diagram where you don't need to do any integral. This is just a constant. And for these exchange diagrams, you can show they're just rational functions of the cross ratio. Okay, so here I'm not even doing any milling transform. So you can follow the exact same procedure I outlined earlier for 60 surface defect. So you can write down ansatz, evaluate it, and then impose supersymmetry condition, and you find these two-point functions are completely fixed. And you find the general results are just rational functions. So this is quite unusual because usually you would have some, at least like some polylogs and stuff. So in this sense, like this is like a very nice setup where which you can regard as the simplest defect CFT. Okay, now another setup I want to mention is the giant graviton correlator. So we actually just put out a paper 2 days ago. So we are looking at a system, it's a 4-point function where you have two giant gravitons and you have two light gravitons, okay? And we are going to look at the leading non-trivial at the large n. So was there a question? Okay. So again, you have, tree level, you have these similar contributions from bulk exchange along the geodesic line of the giant graviton and contact interaction. Okay. And again, you apply the same technology, you find all these tree level correlators are fixed. But what's interesting in this setup is that there's actually a hidden symmetry. So there are infinitely many of these two-point functions, but you find they can be all packaged into a generating function. And this generating function essentially is the lowest correlator, and you uplift it into 10 dimensions. But so this uplifting or hidden symmetry actually was already known for 4-point functions when they are all light. But here the interesting thing is that you can also do it for extended objects. You find some defect version of this generalization. So once you have this generating function, you just do some Taylor expansion and you can get all the other correlators. And what's also very interesting is that although this symmetry was, we found it first at strong coupling, you find that it also holds at weak coupling. So at weak coupling, you can compute these giant graviton correlators by using Lagrangian insertion. So there's the notion of integrand. And you find that this hidden symmetry actually allows you to start from the lowest correlator and then get generating functions for these integrands at every loop order. Okay, so I think I'm using up all of my time. So let me just quickly summarize and talk about something we can look into the next. So as I already mentioned a number of times. So these techniques are very general, and there are actually many other interesting theories we can apply these techniques to. And on the other hand, from these results I showed you, there are already a lot of theory data which we can extract, and also some interesting mathematical structure to uncover. So the hidden conformal symmetry I mentioned for giant gravitons was one of the examples. And here I'm focusing on 2-point functions with defects just for simplicity. But it's conceivable that we can also apply these techniques to higher point correlators. So in the defect-free case, this has already been carried out, and we can go to quite high numbers in terms of insertion points. And this extension is quite interesting from the perspective of amplitudes, because usually there are these interesting features of amplitudes show up when you go to higher multiplicities. And here another thing is that we only look at that defect correlators where you have only one defect. But you can also try to include more defects, yeah? And an interesting starting point would be 4-point functions of 4 giant gravitons, right? So that would be like 2 defects. It's a good starting point because it's also local, 4-point function of local operators. So you can leverage this dual interpretation. The last point I want to mention is that so far we've only considered setups which are, in some sense, probes. Although, like this real projective space is a bit non-perturbative because you need to do a Z2. But in any case, an interesting extension for future would be to develop also bootstrap techniques for defects which can back react to the geometry. So, for example, you can then use these technologies to consider like black holes in ADS, and you can compute, correlators of those with light gravitons. So I think I'm going to stop here, and thank you very much.
Thank you very much for your very instructive talk. It is not so simple to present so technical result. So questions, please.
Maybe I can ask some question in the meantime.
Yes, please.
Yes, please.
Yes, thanks. So yeah, I'm indeed interested. How are you going to extend it to higher points? Because it looks like for 2 points it's, well, I don't say it's simple, but it looks like it's more straightforward. For 3 points, you will have to account much more contributions.
Right. Yeah. So for 3 points, yeah. So kinematics is going to be more complicated because now you have more cross ratios to worry about, and also if you want to just follow this this prescription or this algorithm, you need to include more diagrams in your ansatz. So I think it's probably still doable if you want to look at 3-point functions, but I think going beyond that, it would be useful to use some insights from amplitudes. So you can try to get some sort of recursive method where you can recycle higher point amplitudes. So essentially, what I'm saying is that you can try to use like factorization. So that's like one naive way of implementing recursion. So at least without defects, that has been very helpful. So for example, yeah, we can use this compute like 6-point correlators.
I see.
Are you happy with this answer, Alexei?
No, of course I'm happy. I'm just thinking, well, it's not like I have some picture in my head yet, but I believe that you can do it. because of in standard diagrammatics, usually when we go from 2 points to 3, let's say, points, there are too many things to account. But yeah.
Right.
So are
Yeah.
you planning to do it in some short time?
I'm not sure. There are also many other interesting extensions. So
I
yeah,
see.
I think it's doable. At least, go from 2 to 3. It's definitely doable. But go one step further to 4 point, it's going to be difficult. And the question is how much you can learn by looking at 2 and 3 points. Yeah.
I see. Okay, thank you.
More questions? Maybe I will ask you more general questions. And suppose we have somehow the breaking of conformal symmetry. So we not work with n equal 4 super young means, but some theory which are more closed. For example, n equal 2 super young means theory or something else. What is your answer to generalization of your results? Is it possible or it is difficult to do? What do you think?
Yeah, that's an excellent question. So it's going to be very different because a lot of what I said depends on the fact that you have conformal symmetry. Also ADS-CFT, where, for example, n equals 2, then yeah, so many of these techniques, they do not apply. But I think the general philosophy is still useful in the sense that one can try to use a symmetry to constrain the form of the observable as much as possible. And then, well, I don't know, like make some ansatz, for example, if you, know something about it already, then you can try to use other input to fix your ansatz.
Okay, thank you.
Thanks for the
More
question.
questions, please. Okay, I don't see. Please don't hesitate to raise your hand. If not, I think we can close the seminar. Thank you once again. Thank you.
Thank you.
Thank you.
Okay, thank you.
Thank you.
So honestly speaking, I cannot say that I understand how you easily generalize it to 3 point, but I would be happy to see it.
Yeah, I think, well, if you, I mean, here, like asymmetry charge is also important thing. So if your charges are small, there are not too many diagrams because group theory doesn't allow too many exchanges, yeah? So it's finite number of diagrams from the
Okay, yes, I
local
agree.
perspective.
I mean,
I mean, the bulk perspective, yeah.
Yeah, I see. So you will have to compute more, but not much more, let's say. It will not grow exponentially.
Yeah, so I mean, that's the thing. So I think going to more points is going to be exponentially harder. And so one needs to come up with some better strategy, how to guess it, like before it becomes impossible to compute.
I see. Okay. I see. Okay, good. Thanks a lot.
Yeah, thank you. Yeah, sorry. Yeah, I thought it's 10. Yeah, I don't know.
Well, I'm not sure. Well, but anyway, never mind. I mean,
Sorry. Yeah, I misread your email because it's written 2100 Shanghai. I read it as Shanghai, comma, 2200.
okay. Sorry.
Yeah, I see. Yes, yeah. Sorry about that. Yeah.
No, but it is okay. Come on, it's fine. There will not any problem.
Okay.
I was worried that I did some, but you see, the point is that this email is computed kind of automatically. Once we fix some time, let's say in Brussels, it's automatically recomputed to everything.
Very nice.
So,
It's
so
automated.
it's not like I bother about every location. Okay, good. Thanks a lot.
Yeah, thank you.
By the
Yeah.
way, just in case, Monday, Tuesday, and Wednesday, I'm not sure about Wednesday, but Monday and Tuesday I will be in Beijing.
Oh, this Monday?
Yes.
Sorry. Yeah. So actually, I'm going to Europe for 3 weeks, and I'm leaving on Monday. Sorry, Sunday early morning. So I guess I will
I
miss.
see.
But
I
are
see.
you going back to Europe any like next month? This month?
Next month, actually not. I will go to Europe end of May.
End of May. Okay. I think I will be in China at that time. Yeah. So I'll only be
Nice.
there. Yeah, in April.
Wow. No, in fact, actually, I will go to Beijing tomorrow, but I will go there with my son. So I will be busy until Sunday. And on Sunday, I will just stay there longer until Tuesday to have a seminar and give a seminar in IHEP.
I see. I see. So who invited you there?
Jin Ren or
Who?
Ren Jin. Ren Jin, I think,
I see.
if I speak. Lady who was working with Bob Hold'em on regularized black holes and stuff like this.
I see.
So
Okay,
yeah,
yeah.
a bit of
Enjoy the vacation.
yeah.
It's going to be a bit crowded.
I just don't suggest to meet on Saturday because I will be with my son, so it will be kind of busy.
Yeah, it's fine. I mean, we can meet other
Yeah.
time. Yeah, elsewhere. Yeah.
Okay. Good. No, I just
Okay.
wanted to mention because
Yeah. Otherwise, we can meet up. But unfortunately, yeah, I'm leaving. Yeah, on Sunday very early in the morning. Yeah.
it's great to be in Europe, so
Yeah.
why not?
Yeah.
Just this 10-hour flight, but it's okay.
It's not that bad. I mean, it's less long compared to flying
Yeah.
to. Yeah.
Okay. Good.
Okay.
Then
Great.
see you around.
Yeah, it's nice seeing you. Okay. And yeah, thanks.